In this video, we're going to look at logarithmic functions, and we're going to see how they relate to exponentials. So we're going to start by looking at that relationship, and then we're going to look at some basic properties of logarithms. Okay? So if you recall, every exponential function in the form f of x equaling a to the x is a one-to-one function. And so if you recall what the graphs of these looked like, we basically were looking at either increasing or decreasing functions that were entirely above the x-axis. And so we can easily see that this is certainly going to pass the vertical line test and the horizontal line test. We call the inverse of an exponential a logarithm, and we're going to denote it this way. F inverse of x is equal to log base a of x, where a is the base of our logarithm, and just like with our exponentials, a is greater than 0 and a cannot equal 1. So we define the logarithm as follows. Log base a of x is equal to y if and only if a to the y is equal to x. And again, this if and only if means this arrow goes both ways, meaning I can start with an exponential function and turn it into a logarithm, or I can start with a logarithm and turn it into an exponential. This is what we call the exponential logarithmic equivalence. And this is probably one of the most important properties of logarithms, because we're going to use it not only to switch back and forth between the two different forms, but we also use it in solving equations, in simplifying the expressions, and as well as graphing. Okay? So you're definitely going to need to know this form. Okay? So one of the first things we're going to look at is just changing between logarithms and exponents. So we want to use that definition, that exponential logarithmic equivalence, to change between the logarithm form and the exponential form. And so here's just a few examples of this. Okay? So in this first one, we have log base 8 of 8 is equal to 1. And we want to change it, because it's in a logarithm form, to an exponential form. And so here again, looking at our equivalence, once we know what the base is, and the argument, and the answer, we can just rewrite using those different pieces of the logarithm. So in this case, our base is 8. We're going to raise that to the answer, which is 1, and this is going to equal the argument. Okay, and so there's our exponential form, and we can see that that makes sense, right? 8 to the first power is definitely 8. Okay, same thing here. If we look at log base 5 of 25 equaling 2, we can see that 5 to the second power is going to equal 25. For log base 4 of 1/64 equaling negative 3, again, 4 to the negative 3 is going to equal our argument, 1 over 64. Okay. And then for that last logarithm, log base 3 of 81 equaling 4, says 3 to the 4th is going to equal 81. Okay. And then the nice thing here again is, when we go from logarithm form to exponential form, we can actually check that we did these right, because we know how to simplify exponentials. Now going the other direction, we just have to be a little more careful, because at this point we don't really know how to evaluate logarithms. So when we go backwards, we're going to get an expression, but there's not an easy way to check other than going back over to this and making sure we've put things in the right places. Okay? So here, if I start with the exponential form and I try to go back to the logarithm, again I need to know what the base is, what the answer is, and what the argument of the logarithm are. So if I'm looking at 8 to the 2/3 power equaling 4, this says that log base 8 of 4 is going to equal 2/3. Okay. In the case of 7 cubed equaling 343, again, base to the answer equals the argument. So log base 7 of 343 is going to equal 3. For the next one, 6 to the negative 2 equaling 136. So log base 6 of 1 over 36 is going to equal negative 2. And then for the last one, I threw this in here because if you remember, not all of our exponentials have nice rational or integer bases. In some cases, we have bases that were irrational, like the e. So if we look at e to the x equaling 2, we can again see that log base e of 2 is going to equal x. I'm going to put a little star by this one because now we're going to look at some properties, and this one falls into some of those properties that we're going to look at. So some of these basic properties that we're talking about are ones that we're going to use to help simplify some expressions. And so here I've listed the main 6 properties that you're going to see. And we're going to look at some other ones later on when we start looking at equations. But for simplifying expressions, these 6 properties are the ones we want most. Okay? The first couple come from some of our basic properties of exponentials. So if we look at log base a of 1 equaling 0, if you recall from our exponentials, a to the 0 is equal to 1. So it didn't matter what our exponent was, it didn't matter what our base was. If our exponent was 0, this always came out to be a value of 1. And so the same is going to be true for logarithms. It doesn't matter what the base is. If that argument is 1, the value of the logarithm is always going to be 0. The second one is kind of similar. So if we look at what this says in the exponential form, it says a to the 1 is equal to a. And again, that's true for, again, any base a. So if my base and the argument are the same, the logarithm is always equal to 1. Okay. The next one actually combines kind of true properties that we'll see later. One that we've just looked at, the log base a of a equaling 1, but also one that we'll see a little later when we start looking at some of the properties for solving equations. And this basically just says that if the base in my logarithm is the same as the base in the argument, then whatever that exponent in the argument is what my value of the logarithm is going to be. And again, here, if we look at it in the exponential form, it doesn't say a whole lot because it just says that a to the x is equal to a to the x, meaning this a to the x is equal to that argument. Okay, and we can see that that is definitely going to be true. Okay. Number 4 looks at the inverse of this. So again, you have to kind of remember that logarithms and exponents are inverses of each other. And so number 3 is basically saying if f is my exponential and f inverse is my logarithm, this is basically f inverse composed with f of x, where f equals a to the x and f inverse equals log base a of x. And if you remember from chapter 2, when we were looking at functions and their inverses, it said that if I compose a function with its inverse, I'm always going to get that domain variable. Okay? And so here is the same thing, just going the other way. So if I look at f composed with f inverse, then I should get x. And again, these being my f and my f inverse. Now the next two are ones that are more definitions than they are properties. Okay? This first one, if we see a log of x that doesn't look like it has a base, this is actually referring to log base 10. Okay? This is what we consider our common logarithm. In many of your sciences and some of your later math classes, you're going to see a lot of notation that looks like log of x or log of 20 or log of something. And it's not going to have a base written there. You will almost never see it written this way. Anytime you see this notation, this is just meaning I'm looking at a base 10. Okay. The same thing is true with number 6. If I see ln of x, this just means I'm looking at a particular log where the base is e. So again, that special case that we talked about, our natural exponential, we're looking at the inverse of that function. Okay? And this is what we call our natural logarithm. Okay. And again, it's called the natural logarithm because it's the inverse of our natural exponential. Okay. And so these are different properties that we're going to see that are going to be used to simplify expressions. Okay. So for example, let's say we had the expression log base 5 of 125 that we want to simplify. Okay. Well, looking at this, it doesn't look like any of our properties right away. But if we can rewrite it so it does look like one of these properties, then we can simplify it fairly easily. Okay. And here the thing to notice is 125 can be rewritten. This is the same as 5 to the third. Okay. And so here we can see this actually looks a lot like our property 3. So the base in my logarithm is the same as the base in the exponential, and so when I simplify that, I'm just going to get that exponent. Okay. Some of these are not quite as nice. Okay. So for example, let's say I wanted log base 27 of 3. Now, just like in the previous one, what we almost think to do is to look at the 27 and say, well, 27 is 3 cubed. But here, we don't have a property that changes our bases. We only have a property that's going to affect the argument. So here, I need to somehow rewrite the argument so that it is 27 to a power. Okay? And so here I can see that 27 to the 1/3 is going to be the same as 3. Okay? And then again, using that same property, number 3 over there, we can see that that's going to give me a 1/3. Okay? One of the things to notice is if my argument is bigger than my base, I should end up with whole numbers or integer values. Okay? If my argument is less than my base, then I should get some fractional powers. Okay? And so these go back to what we were saying about our exponent graphs increasing and decreasing. Okay? And so later we'll see some properties where we're going to combine some of these things and again be able to solve equations. But these are just the first steps. 0 back into our polynomial form, we see that we get 9. For the end behavior, here our degree is 3 and our leading coefficient is 2. So odd degree this time, even leading coefficient or positive leading coefficient. So we're looking at end behavior that has opposite sides. Okay. So for our graph on this one, again, we'll start by labeling our graph. Okay. So our zeros, we have 1 at 1/2, 1 at +3, and 1 at -3. And our y-intercept is up here at 9. Our outermost ones to the left there, we're going to -infinity. The right, we're going up to +infinity. Okay. All of our multiplicities are odd, so we're going to pass through each of them. So coming from the negative side, I'm going to pass through the 3 there. But notice, to get to this 1, I'm going to have to go through my y-intercept. So here I'm going to actually change the slope here just a little bit, because I'm going to come through that point and then go to negative infinity. Okay. Now it could be I come up and this is a high point on this side and comes back down. But since that's so close, I'm going to draw it this way. And then at a half, again, I'm going to pass through. When I get back to positive 3, I'm going to pass through again. And so there would be the sketch of my graph. So in this first section, like I said, you're going to be asked to do something similar to what you see here, where you are given different polynomial functions, both in their factored and in their polynomial form, and you have to go through and be able to come up with a picture for the graph. Again, to do that, you're basically looking at what are the zeros, what are their multiplicities, what's the end behavior, and then knowing the multiplicity and how the end behavior react to that information, what the graph looks like. Zero back into our polynomial form, we see that we get 9. For the end behavior, here our degree is 3 and our leading coefficient is 2. So odd degree this time, even leading coefficient or positive leading coefficient. So we're looking at end behavior that has opposite sides. Okay. So for our graph on this one, again, we'll start by labeling our graph. Okay. So our zeros, we have 1 at a half, 1 at positive 3, and 1 at negative 3. And our y-intercept is up here at 9. Our outermost ones to the left there, we're going to negative infinity. The right, we're going up to positive infinity. Okay. All of our multiplicities are odd, so we're going to pass through each of them. So coming from the negative side, I'm going to pass through the 3 there. But notice, to get to this 1, I'm going to have to go through my y-intercept. So here I'm going to actually change the slope here just a little bit, because I'm going to come through that point and then go to negative infinity. Okay. Now it could be I come up and this is a high point on this side and comes back down. But since that's so close, I'm going to draw it this way. And then at a half, again, I'm going to pass through. When I get back to positive 3, I'm going to pass through again. And so there would be the sketch of my graph. So in this first section, like I said, you're going to be asked to do something similar to what you see here, where you are given different polynomial functions, both in their factored and in their polynomial form, and you have to go through and be able to come up with a picture for the graph. Again, to do that, you're basically looking at what are the zeros, what are their multiplicities, what's the end behavior, and then knowing the multiplicity and how the end behavior react to that information, what the graph looks like.